Welcome back to the third installment in our series on troubleshooting transmission systems with the Freedom Communication System Analyzer. Again, as we review, the scenario is the system you're responsible for. You've been told it's broken, it's down, and we're going to figure out how to determine where the problem is. In our first installment, we isolated the radio electronics. We tested the transmitter and receiver to determine if everything was functioning properly. In the second installment, we talked about testing the RF networks that connect the electronics to the cables and antenna. And so in this case, we hooked up and we used a tracking generator to test the duplexer. Finally, in this installment, we're going to hook up to the cable and verify the function of cable jumpers, lightning protectors, adapters, and antenna system. Try to determine where the fault can be found. We'll be using the cable fault locator and the tracking generator functionality. There's two types of measurements we'll be doing, and so we're going to break this section into two parts, Part 3A and Part 3B. In the first segment, we'll talk about the distance to fault measurement. In this case, we'll use our cable fault locator, which is a frequency domain reflectometer. Its purpose is to show the return loss as a function of distance. So try to tell us where down the line we have a problem. In Part 3B, we'll be looking at the frequency response or sweep. In order to use the tracking generator for this, we're going to need the optional return loss bridge kit, which gives us the ability to measure reflected power. What we are going to do with this instrument is determine what the return loss is as a function of frequency. This will enable us to find out if the antenna system is properly tuned and working at the frequency that we're operating at. What is return loss? And return loss is defined as a measurement of how well devices or lines are matched. Usually this is expressed in dB when we look at return loss. If there's a good match, then the return loss will have a high value. The return loss is related to the standing wave ratio. We will look at charts that show you how to convert from return loss to SWR or VSWR, and it's also related to reflection coefficient. An increase in return loss corresponds to a lower SWR. Okay, let's talk about distance to fault measurements. There are two ways to do this. The old way, as I call it, is the time domain reflectometry. Basically, you're sending a pulse down the cable and you're measuring the time it takes for the signal to come back to tell you how far down the line it traveled before it was reflected, and then the amplitude of that reflection tells you how much of the signal was reflected. This method does have some limitations, especially if you're looking past a large discontinuity, looking down further down the cable. It can be difficult. This is a very good method, was used for a very long time because of the electronics involved were fairly straightforward. The new and better way is frequency domain reflectometry. In this case, we are sweeping the cable across a range of frequencies and using mathematics to decipher the data that comes back. And basically what you end up with is a view of the entire length of the cable and the amplitude or the magnitude of the mismatches along the length. Another benefit here is that it does not require a return loss bridge. You can use a simple splitter or power divider. All of our full screen instruments can be found by pressing the blue instrument button in the upper right hand corner. This provides a selection menu. This is the tracking generator. If you'll press the more button, you will find the cable fault locator. If you're following along with me, I strongly recommend you go into Test Presets Load Factory Configuration to return your instrument back to a default state. If you get a pop-up message about the preamplifier, simply press the cancel key. Alright, so the main things that we need to set up are the center frequency. In this case, in our scenario, we're going to pretend we're operating exactly at 800 megahertz. then we need to enter the velocity factor of the cable. This can be found on the manufacturer's data sheet for the cable. So look at the cable, look at the part number, Google the part number and data sheet, and you should find something that says velocity factor or velocity of propagation. It's in percent. In this case, it's 85%. So we will enter a value of 0.85. I'll do that right here, 0.85, and press enter. The next step is to put in the type of units we want to use. Distance in units, we're going to set that to feet instead of meters. And finally, we need to tell it the maximum length. In this case, I know I have a cable that's shorter than 100 feet. So this value needs to be at least as long as the cable. If you don't know exactly how long, just make this longer. This will determine what length is shown on the right hand side of the screen. There we go. Now, once we've entered all these values, we select Analyze, and we'll need to calibrate out the losses in the splitter and the cables going to the splitter. So when you press Calibrate, you will get a message telling you how to set up the cable fault locator. In your accessory kit with your R8100, you will have received our standard accessory, which is a microcircuits 3 dB splitter. Comes with 2 short test cables. It comes with a 50 ohm load with a chain and a screw that allows you to attach the load to the splitter so you don't lose it. And so this is instructing you to hook up your cables to 2 ports and to put the load on the last one. If you have our optional return loss kit, or you have your own other splitter you can use, and this is a picture of the one that comes with the return loss bridge kit. And these are all N-type connectors. That kit also comes with cables that fit it, and also there's an N-type 50 ohm load. Once you've done that, you simply press continue, and you will notice the progress bar at the bottom of the screen as it calibrates. Once the calibration process has completed, it will instruct you to disconnect your 50 ohm load and connect to your cable under test. I'm doing that right now. Again, you're going to want to make sure that that connection is nice and tight, otherwise it will have an impact on the measurements. Okay. Now I'm going to press continue. At this point, I can now press the Analyze button, the soft key here, and I can choose either to continuously sweep or single sweep. We're just going to do a single sweep. And again, you'll see the progress bar going across until it has completed the scan. Now that the sweep is complete, we can place a marker at this highest point and see that it's located a little over 75 feet down the cable. So, and in fact, this is a 75-foot piece of cable. We can see that the return loss at that point is less than 1. So if we'll look over here at this return loss table, return loss of less than 1 is showing that we're reflecting almost all of the power. And in fact, I've got the end of this cable open, so all of the power should be reflecting. And so we see that here in this case, that the cable end is open and we're reflecting. And as we described earlier, we're able to see the return loss as a function of distance. And then you might be asking yourself, okay, so do I need to worry about these peaks here, or what is the typical return loss for a lightning protector? What is the return loss for an adapter or a coax cable? On this next slide, I have some values that you can look for, and let's move our marker again. Okay, 24, nearly 25. So there's something going on at approximately 49 feet in this cable. That's about 25 dB is what we would expect for a connector. There is no connector, but there may be a slight kink, or maybe the cable has been bent. But you can see very clearly where all the discontinuities. You can see the good cable is down here, and you see discontinuities. And again, you might now wonder, what is the equivalent to 25 dB? If I look at the chart, it is 1.12 for a Viswar number, which means that only 0.32% of the power is being reflected, so probably not a major concern. Okay, so what I'm going to do next is I'm going to put a 50 ohm load on the end of the cable to show you what it looks like when there's most of the signals being absorbed at the end. And finally, we will put a portable antenna and show you what you can expect with a portable antenna. This is a result of a sweep with the 50 ohm termination on the end of the cable. You can see much less pronounced return loss spike here. It's actually no longer the peak, and you can see the value is right at 30 dB. If we look at our chart, 30 dB, 1.07 to 1 on our Viswar. Excellent. Very good match. Obviously not perfect, but very, very close match. We're only reflecting approximately 1/10 of 1% of the power. Okay, so now I'm going to hook up a 7800 and GPS portable antenna. We would expect approximately 6 dB return loss for a portable antenna. For a base station antenna, you're typically looking at 14 dB or better. With a small portable antenna, especially without a proper ground plane, 6 dB is what we would expect. So let's take a look. Here we have it. So now I have the portable antenna hooked up to the end, and you can see that at, again, a little over 75 feet, I'm looking at a little over 5 dB of return loss. Again, we'd expect about 6 dB, but this antenna is not mounted to a radio. There's no good ground plane, and so it's not quite as good as a performance as you can get with a portable antenna. Again, 6 dB for a portable, 14 dB minimum for a base station antenna. And now I'm going to show you that we can also determine the total return loss in the cable. It's being hidden from us at this point because we are counting for cable loss in the calculation for the return loss. But if I tell it to not account for the cable loss, we can actually look at how much cable loss we have, how much power is being lost just in the cable. For that, I'm going to go back to an open circuit and turn off the compensation for the cable loss. Here's the result. Again, I've created an open circuit, and you'll recall the last time we did that with the cable loss compensation, we ended up just under 1 dB. You'll notice here now that we're looking at 6.5 dB. How do we know if that's anywhere close to correct? Well, let's take this length. Let's take from the manufacturer's data sheet, we know that the cable loss should be approximately 0.044 dB per feet. Multiply that, we get 3.33 dB. Now remember, the signal's going all the way to the end of the cable and coming back, so it's actually measuring twice the cable loss. So if I multiply 3.33 by 2, obviously I get 6.66, and you can see we're getting 6.5, so which is very close to the theoretical or specified amount. So there's no major flaws in this cable. Obviously there's an open circuit and the signal's not being radiated, but the cable itself is fine. In our next segment, we'll talk about looking at the return loss instead of across distance, across frequency. At this point, we've swept the cable and antenna and determined whether or not there were any problems to be investigated along the cable. Let's make the assumption that we didn't find anything, but we're not getting a very good return loss measurement at the end of the cable, indicating that there's a problem either at the connection or that the antenna is not tuned properly, especially for the frequency that we're operating at. So now we want to look at the frequency response of the system to try to determine if perhaps the antenna is not tuned properly or has been damaged in some way. The way we will do this is to look at the frequency response using the tracking generator, and we are going to need a return loss bridge kit. We're going to need to have the ability to isolate the reflected power to feed it back into the instrument. In order to do this, we set up the tracking generator. For more details on using the tracking generator, see part 2 where we looked at tuning the duplexer. I'm going to move a little faster here, but the main thing right now is we need to set the center frequency and the span or start and stop frequencies to determine the area where we want to look at. Now in this case, I have an antenna that's a 7800 and GPS, so I've set a fairly broad span. I want to be able to look at the 700, 800 megahertz. I've actually started at 475 megahertz and gone all the way up to 2 gigahertz, since we'll be looking at the 1.3 gigahertz for the GPS. So very, very broad. Once we have those set, the next step is to be able to calibrate out the losses in the RF coupler or return loss bridge and the test cables. And the way we do this is we hook up the coupler as indicated here. We also have a great app note on the website, and then we leave the device under test port open, and I will do that. I have that all set up right now, and I'm going to go in here and go to the last screen, press normalize and on. Okay, what you'll notice now is that the line has turned from yellow to light blue. It says trace normalized, and now we sit right at 0. So all the losses that are induced by the system in the instrument itself or in the coupler or in the cables has been compensated for. Once that's done, we then connect our cable. Again, we can still be on the ground connecting to the cable that's going up to the antenna. So what I'm doing right now is I'm connecting to the end of my 75-foot cable, which we've already determined is looking pretty good. I've got that screwed on. I'm making sure it's nice and tight. And at the end of the cable, I have my 7800 portable antenna. Again, not a very good ground plane. What you'll notice is right now what I'm doing is I'm touching the base of the antenna, the SMA connection, to try to provide it a little bit better ground plane. But you can see as I shift my finger up and down the antenna that the frequency response is changing quite a bit. So again, this is not ideal scenario, but let's take a look here. So first of all, let's turn on a marker. Come here to marker mode, select absolute. You can see the marker here. I'm going to change the marker style or type to a vertical bar, make it easier for us to all see. And I'm going to move this marker over here towards this relative low, and you can see this relative low is somewhere in the 800, low 800 megahertz, so that's not too bad. So really, when I'm looking down at the bottom here, I'm looking at negative 14, and if I add 6 to that, I'm really looking at a return loss of 8 dB. And so really 6 dB operation from the high 780s. Oops. So 14, 12, okay, to 921. So this particular portion of the band right here is where we're resonating, at least as good as a theoretical portable antenna. Okay, so now we have, from the ground still, determined that this particular, of course this is not a very good antenna for a base station, but it is performing as it should. Had we determined that we were not radiating enough power, or not as much as we should be, then the next step, we send a tower crew up to the top, and they can bring that antenna down, and we can hook up the antenna directly to the instrument. And now we no longer have to account for the cable loss. But up until now, we have not had to replace cables. We have not had to climb towers, not had to guess. Everything has been pass, fail, and then we were able to determine the distance to the fault if there was one. So the practice of just swapping out parts really is no longer valid. That is the benefit of using the cable fault locator first, and then looking at the return loss across frequency to make sure that the antenna is performing properly. And now you should have, using all three steps that we've covered so far, testing your electronics, testing your duplexer or RF network, testing your transmission lines and antenna, should be able to find the problem. Thanks for watching this series. If you have questions or want to watch other videos or find our app notes, the information is there on the screen. I'd love to interact with you if you'd be interested. And hopefully I'll see you again in some other videos./Thanks for watching.
To find our representative near you, visit www.freedomcte.com/sale.